Today we are looking at the truth behind helium. Many statements about helium have been made over the years and repeated so many times that they're now considered to be fact. These include the fact that helium is considered to be a key element in the energy transition. The world's supply of helium is running out. New helium discoveries are changing the script. Helium concentrations only need to be more than 0.3% to be pay, and helium plays exist in Alberta and can be economic. What we're going to do today is to consider 10 of these classic statements to see whether they are really true or false. 10 key questions. Question number 1, is helium a key element in the energy transition? And the answer to this is no. Helium-4 is radiogenic. It's far more common than helium-3 and makes up almost 100% of helium on Earth. It's more important economically, and it's produced through radioactive decay. It makes up around 23% of the mass of the universe, and it is not a viable energy source. Stars do convert hydrogen into helium-4, but it's this nuclear fusion that powers the stars. And in fact, it's the reduction in mass when it's burnt that creates the energy. Helium-3 is a light, non-radioactive isotope, primordial helium. And this is rare on Earth, possibly abundant on the Moon, deposited by solar winds. And there are only 2 parts per million in natural helium gas to 20 parts per million in the Earth's crust compared to helium-4. So the fusion of helium-3 atoms does release large amounts of energy without leading to radioactivity. So that it is a great source of energy, but it requires very high temperatures. It currently takes more energy to separate out helium-3 than is produced by fusion, and there is considered to be no chance for helium-3 power plants until post-2050. Question number 2, what is helium used for? Well, the most important use for helium is in magnetic resonance imaging due to its very low boiling point. It's also used as a cooling medium for superconductor magnets, also in places like the Large Hadron Collider in Switzerland, and it's very unreactive, so it's used to provide an inert protective atmosphere for making things like fiber optics and semiconductors and for arc welding. It's also used in high-speed internet devices. It's used for cleaning rocket fuel tanks and in microscopes, but less than 10% of helium production is used to inflate balloons of all kinds, including balloon animals. And we've got a pictorial representation here of the global uses of helium, and we can see that the cryogenics and welding make up the most part, heat transfer and pressurization as well, and party balloons are sitting down there at about 8%. And the world consumption of helium we can see is dominated by China, Northeast Asia, Europe, and in North America. Question number 3, is helium running out? And this is definitely a truism. The answer is no. Helium is formed mainly from radioactive decay, and it will leak off from Earth due to its extremely light mass unless it's trapped underground. And it's mainly produced as a byproduct of natural gas. So as gas production has increased, particularly from the unconventionals, this has meant a lot more helium production. And the Earth's reserves of helium are plentiful, and even the recycling of helium is improved. So there is more helium wasted by one large-scale LNG plant than used in the world's party balloons. So it is not the shortage of helium that creates problems and creates confusion in the market. It's imbalances. So it's whether the supply and demand actually allow the helium to be released. And there's been a lot of controversy about this over the last few years. That has been what affects the price. So as the price has gone up, people have assumed that there must be shortages, but generally speaking, it is literally a supply and demand scenario. So where are the world's existing helium reserves right now? Well, first of all, where does helium come from? And the main source of produced helium is as a byproduct of natural gas production. So helium leaks into reservoirs from underlying radioactive basements. If we look at this diagram here, we can see we've got some igneous intrusions sitting down here with radioactive content within them, and the radioactive decay leads to the production of helium, particularly from uranium. So we'll end up with a lot of helium atoms here. Some of these can pass up through faults and fractures as well, and then they will gradually accumulate in a reservoir just like natural gas would do. And then there'll be secondary migration from there, either through ground mass of rocks or even dissolved in water, and then they end up mixing with a natural gas reservoir near surface. And then this can be produced along with the natural gas, and that's one of the ways that we generate a lot of helium. So helium is also associated with high nitrogen values. So if you have nitrogen producers like certain hot springs and certain anticlines around the world, particularly Cabiaku in the Zagros Mountains, then if you have the nitrogen, there's a very high correlation, over 90% correlation with significant helium values as well. And then generally speaking, helium can also be produced as a direct decay product of radioactive rocks, and places where this occurs are places like Utah and South Africa. So you may be able to produce it without having to produce it along with natural gas. So who's producing most of the helium around the world now? Well, the USA currently produces almost 50% of the helium production, 2.8 BCF. But this is estimated to decline to around 20% of global supply over the next decade. So most of that helium right now and over the last few years has come from the Bureau of Land Management and connected Hugoton Panhandle Complex, which makes up about 2/3 of US production. And I will show you more on that in the next slide. But now the US is selling off this reserve, and the complex is in decline. So by the late 2020s, it's expected that Qatar, Russia, and Algeria will produce around 75% of the global helium supply. So Russia has a big Amur project, and Qatar's RL project, they will add around 3.7 BCF this year to next year. And there's a variety of other projects around the world which should come on stream within the next 5 years. So you can see here's the diagram showing the decrease in US supply. Here we are sitting in 2021. You can see that the actual amount of the helium that's being produced is going to decline continuing into the next decade. But right now, the United States, mostly extracted from natural gas, is sitting around here at about 61 compared to much smaller production from these intervals. And we can see that Qatar and Algeria here are the other two main producers. So the Hugoton Panhandle Complex is currently producing, and it's one of the largest gas fields in the US, just as a gas field, along with some other fields that are located around it, some satellite fields. So here is a map of the field. You can see there's Colorado, Kansas, Oklahoma, and New Mexico. So it makes up a significant area, not a significant portion of any one individual state. And the different wells here, the different fields, are all connected by pipelines to the series of helium extraction plants, and these move the helium to the storage facility at Cliffside. And it's declining by an average of around 6% per annum. Then there are other US producing fields. So we can see here in Arizona and in Wyoming, and these fields are also producing a significant amount of helium. So, have new helium discoveries allayed fear of a global shortage? Well, the answer is yes, there are significant new discoveries out there, but no, there probably was never a global shortage. So all these scaremongers who are saying you shouldn't be using balloon animals anymore really don't have a leg to stand on, because it was, as we mentioned earlier, it's much more about the supply and demand. So where are these new discoveries? Well, first of all, we have the three big players who are going to come online in the next 10 years, Qatar, Russia, and Algeria. And the Qatar RL helium projects produced 2 BCF in 2018, and they're expected to bring on new helium plants in 2023. And we can see the estimated production here is gradually increasing through time, up to close to 4 BCF by 2029. And most of this helium is coming from the giant South Pars gas field, the biggest gas field in the world. And the concentration is actually relatively low. It's around 0.05% helium. But because of the amount of gas that's being produced, we can produce a significant amount of helium as well. The Russian Amur project, which is being run by Gazprom, which is sitting here in the middle, you can see that that's aimed to come on stream within the next year or so, and then we'll ramp up to around 2.5 BCF by 2026. And then Algeria is producing via LNG, the helium by LNG. You can see the helium concentration here is only about 0.17% from the Hassi Armel field, and obviously the production of helium will depend on the production of the LNG, but there is a potential here for 600 million scuffs per year. And we can see here that on this diagram that the production is estimated to be pretty stable after 2022. There are other projects around the world. So Australia has a plant in Darwin producing a significant amount of helium. In South Africa, and ironically, this is a gold mine that I used to work on. It has significant uranium content within the ore reserves, and as that uranium content has deteriorated through time, it's released a lot of helium, and the helium is mostly dissolved in groundwater within the mining system, and they've actually created new plants within the fields within the Orange Free State in South Africa, and these plants are producing some of this helium now. And they're expecting up to maybe 25 million scuffs per year by 2025. Poland has 16 small helium fields which are producing some volumes as well. And Canada, our own country, has a number of projects ongoing. And the deposits of helium are often in deeply buried traps with little associated CO2, making the extraction and liquefaction cheaper. So there's projects ongoing around Cyprus, Battle Creek, which is spanning the border with Saskatchewan and Alberta, Medicine Hat, Mankota, and together these may produce as much as 140 million scuffs per year. So there's significant volumes in Canada and potential for more. Tanzania, helium was discovered to be bubbling up in geothermal pools in Tanzania, mostly in this area here around Lake Rukwa, and mainly nitrogen was bubbling up with helium content up to 10%. And the company that's working this, Helium 1, they estimate recoverable reserves of up to 140 BCF. However, we have to be a little bit careful here because I think there's significant evidence that these are very optimistic figures. But nonetheless, there's definitely helium values there. But whether it will produce as much as they say is a good question. So what's happened in this area is that you have the African rift, and the rift has split the crust. And volcanic intrusions are heating the rock, releasing helium from these basement rocks. And it's not dependent on co-production, so it can be produced purely as helium from this reserve. Question number 6. Is 0.3% helium enough to be pay? And this is a figure that you will see in pretty much every publication around the world. And common sense really dictates that this would depend on the productivity of the well. If the well is producing almost no gas, then 0.3% of that being helium would make little difference. Little gas, little helium. So the interesting factor, and where this figure came from originally, is that 0.3% or more of helium renders it the most valuable component in natural gas. So the cost of the natural gas compared to the cost of helium, you don't need as much helium to be pay as you do natural gas. So in at least one field around the world, helium is being extracted at 0.04%, and that's still economic. And good examples of this are in Qatar and Algeria. And I mentioned earlier about Qatar producing at about 0.05%, so 1/200th of the gas only is made up of helium. And you can see that Qatar's revenue from this helium, that's such a low concentration, was around $1.23 billion. So that's pretty amazing amount of money considering that it's such a low concentration. And they produced around 2 BCF in 2018. So definitely there's great potential in Qatar from this South Pars gas field and other gas fields in the country. Question number 7. Is helium common in gas reservoirs? Well, that is a yes. So studies of gas samples from gas fields in the US show that more than half of all the gases that were sampled contain more than 0.1% helium. So a lot of them contain something, but only 17.6% of all gases contain more than 0.3% helium. So that's that significant cutoff point where the helium becomes more valuable than natural gas. So if you have pay natural gas, 17%, so only about 85% of the gases will be unpay, and the natural gas will be unpay, so in terms of helium value. So there are some pay helium areas as well, but most of those helium areas, as we can see from this map, are sitting in that Four Corners area and that area that we looked at earlier where the Hugoton Panhandle complex was based. So you can see that it's Texas, Kansas, and Oklahoma where most of them are concentrated. And high nitrogen reservoirs with higher helium content do occur in Colorado, New Mexico, Utah, and Arizona as well. So we can see a lot of areas where there is at least some helium, where these blue colors are. So even though the helium values may be low, there is a lot of helium around in the US as an example. So question number 8, how would you go about exploring for helium? Well, first of all, you should look for radioactive rocks, because helium accumulates due to the radioactive decay product of uranium and thorium, and particularly the uranium. And the joints in the formations at depth, joints and faults, these can provide conduits for the helium to seep towards surface. And the buoyant decay products of igneous and crystalline basement rocks will travel up fractures and faults into porous reservoirs that overlie them. So as long as you have a seal, they're going to get trapped. So you should be looking for radioactive rocks, seals, and ideally high nitrogen concentrations, as we've already mentioned. So a nice approach for this would be to use play-based exploration. So this is the PBE system, so very similar to what you do if you were looking for oil or gas. And so the things to look for would be radioactive basement. So I've got an example here from Western Canada where we've got a map of where the radioactive basement is. So these brown colors here. So those brown colors would be the areas that you'd want to target in our 2 provinces here, because they're obviously going to have the highest decay products. Then you want to look for seals. Then we've got a map of the evaporite seals sitting in here, the prairie evaporite and similar. And then ideally you'd want to find some host gas fields as well. You can see there's a lot of these fields in Alberta, less fields mapped out in Saskatchewan, but nonetheless, if you overlay these 3 maps one on top of the other, the sweet spot where you have the seal, the source, so the radioactive basement, and you have the reservoir, so the gas reservoirs would be in this area here. So stretching up to Fort McMurray and stretching down past Leduc on this eastern part of Alberta. So that's another way that you can explore for helium. I am going to show you a third way, but we'll come to that in question 10. So question number 9, what is the potential yield of helium from granites? Well, 360 cubic centimeters of helium is produced per cubic meter of magmatic rock every million years. And that's a very long time scale. 1 gram of thorium produces 24,000 atoms of helium, and 1 gram of uranium around 100,000 atoms. So annually, around 1,125 times 10 to the 30 helium atoms are created in the mantle and crust, of which a small proportion relatively escapes to the atmosphere. And it takes 8 times 10 to the 28 to fill a blimp, which is around 539 kilograms of helium. So we have many, many blimps. We have 100,000 blimps worth of helium being created annually in the mantle. And these geothermal hot springs may be charged with helium that comes from these granites. So I've got some example here where these hot springs, the Chumathang hot springs in India, which are fueled by hot granites, do have a decent helium concentration, although it may not actually be economic. There's a significant amount of helium being produced. So the last question we're going to ask, is there helium potential in Alberta? And the answer is a definite yes. So me and a friend from IHS, we did some work which we presented at an earlier conference where we looked at the helium values across the province. So we mapped them out in good old AccuMap, and what we were able to do is to produce this map of the helium concentrations. And just to highlight a couple of examples here, we used 800,000 wells, and we actually used 180,000 of them to create this map. We identified a series of the hotspots, and so the leads that we have here is seal. So the seal area, you can see there's a really nice concentration sitting in here, which has not been produced at all. So there's helium potential here, helium potential along the Rockies margin, and there's definite helium potential sitting down here in the Medicine Hat area. And Medicine Hat actually has their own production facility producing helium. So they've not only proven this, but they're going ahead and producing this. And that extends over into Battle Creek area, sitting in here in Saskatchewan. So there's significant potential here for helium, not only in the areas where it is being produced, but in other areas where we see these hotspots as well. So just to conclude, there are many myths and legends related to helium. There is no shortage of helium, only sporadic supply challenges. Alberta and Saskatchewan hold high potential for helium production, and I suggest using several different exploration techniques to combine them to assess helium prospectivity in any one area. And it's quite possible that geothermal energy sources, if we're drilling deeply into the subsurface, could also hold helium potential as well. So I'm going to say thank you very much for your attention, and I'm happy to take any questions.